series of basics of software defined radios and practical applications. We are covering the fourth part of the software defined radio architectures. Previously we had seen heterodyne, homodyne architectures, their combination, digital life heterodyne structures which contains the benefits of homodyne structures also. Now we want to have a look at the concept of SDR when we want to do the sampling directly at the RF frequency. So what are the requirements, what are the limitations? This is what we will be covering in this lecture. So architectures to alleviate limitations of DAC and ADC. By using the quadrature channels, we have already reduced the bandwidth requirement by half, means I and Q channel, both of them are carrying half of the bandwidth which was required for the full complex signal. So we are already reducing some of this limitation. Now what is the impact of bandwidth of the signal of the DAC? Till now most of the discussion we have done, they were in the terms of single band. A sinusoidal signal is coming, what will be the up conversion, down conversion, how we will choose the frequency, this is what we have covered. Now let us have a look at the bandwidth impact on DAC and ADC performance. First of all, let us remember our Nyquist-Shannon theorem. So Nyquist theorem, we had seen maximum frequency component, if we have, then our sampling frequency should be more than the twice of our incoming maximum signal frequency. Now Nyquist-Shannon theorem says for the band limited signal, the frequency sampling frequency should be more than equal to 2 times of signal bandwidth. Now when we say signal bandwidth, it is the band limited signal. So we are talking about minus b/2 to b/2 if it is at the base band. So this we have to remember now when we are talking about the band limited signal. Another thing, whenever we are sending any signal and through DAC, sampling it, and or we are receiving in a receiver and we are getting back our digital data from the analog domain using ADC, then whatever we have discussed before, it was in terms of single band signal. So we were talking about a single band signal and then we had said, okay, this is a signal and let us do the quantization, etc., etc. Yeah, so it was the amplitude. Now this signal, suppose it has a bandwidth, how will it impact in the digital in the frequency domain? So for this signal, which is the sinusoidal signal, in the frequency domain, it appears as, let us say it is FRF as a single tone, right. So your DAC, which is able to take this highest amplitude, this highest amplitude is defining the power which it can take. So for a single band, that power is concentrated in this frequency. Now suppose you have 2-tone signal, then or you can say that this becomes the bandwidth of this signal, then these both of these signals, they contribute to that power and the ADC is reaching their highest level of amplitude because of these 2 tones. So suppose this was the noise level and this was the P1 which was because of only single tone, this was the dynamic range. Now when you have 2 signals, the power is distributed between these 2, right. So it will be reduced for sure because it is distributed between these 2 tones and this is your new P2. So P1 has higher SNR for the single carrier, you increase number of carrier, the power is distributed. So the highest point of power with respect to noise is coming closer to the noise, it is becoming lesser and lesser. Now this distance from the highest power to the noise power, it is called dynamic range of any ADC or DAC. So as we can see here, if we have a single carrier, this is being shown here by this arrow, as we keep increasing our bandwidth, the amplitude, the average power will go down, because the whole power is contained within this area now, within this signal now. So, the dynamic range goes down. So, what is the problem with that? That the sensitivity of our signal will go down. What is the sensitivity? We have defined it before, that the ADC should be able to distinguish the actual signal with respect to noise or the interfering signals. So, if this amplitude keep coming closer to our noise level, then it is difficult to distinguish which is our main signal, and maybe our interference signal is higher than this. Suppose it has lower bandwidth, it will have more chance of saturating our ADC, then it will be creating problem in detecting the actual signals. So, now bandwidth can be of two types, like I said. If you have two tone signals, you have two tones and you are still covering the bandwidth B. This is multi-band kind of operation. There are two bands, there are two frequencies on which it is working. This was an example of only two tone signals, but it is possible that it is a multi-carrier signal here, let us say 4 tones here and then 4 tones here also. Now, they have their own bandwidth B1, B2, where it is containing its carriers, it is its own tones, and together by using these two they are again making this bandwidth B. Okay. So, this B contains B1, B2 and the distance between these two. But now, what is the sensitivity requirement for this one? When it was single tone, we have very high dynamic range. When we have this two band system, the dynamic range will go down, and if I want to fill this whole frequency range with the carrier, we want to transmit at all these frequencies, then whole bandwidth is being used, and then in this case our dynamic range will further go down, because it is saturating our ADC and DAC with its whole power. So, the amplitude level is going down. Now, when we are covering all the frequency phase, then we call it broadband transmission, and when we are using selectively some of the frequencies, then it is called multi-band transmission. So, let us keep this in mind, we will come back to it later in the STR. Now, let us go to the concept of sampling, how it affects our architectures there. So, you can see here the relation between the time domain signal and how it is converted back into the frequency spectrum. Xk is representing your complex discrete frequency spectrum, where k is the index of discrete frequency bins. In right hand side again, the time is sample time and time Ts, and Ts is your sampling frequency. So, whenever we are having the multiple of that sampling frequency, we are sampling at a particular points where one time duration is being finished. If we go from if we see in terms of continuous frequency in time domain, and we want to see what will be the complex signal frequency domain, then it is given by an integration as opposed to the summation normally we use there. So, whenever signal is being sent and it is a limited signal, let us say this red lines, they are representing one signal duration, it is a limited signal, then corresponding to that we will have a sinc function, because it is sinusoidal signal. So, because of the windowing function, we can see at Fin, which is at the instance of 1 upon NTS, our sampling points. So, at exact point our data we are able to sample if it is a multiple of Ts in the time domain and 1 upon NTS in the frequency domain. So, these are the particular points we are getting here. If our signals are periodic in nature, but they have disruptive nature, there is a sudden jump as we can see in this case, then we can see this shift, because we use the interpolation filter in the frequency domain. There is a shift here in the data, right, and we will be losing some of the peak points. So, peak points we have lost here, we are not getting the exact frequency location, we are losing some information there. Now, keeping those concept in mind, let us go to the Nyquist frequency criteria. We know that our sampling frequency should be more than the twice of F in max. So, in this figure you can see that this is our signal in frequency domain, and the max will be decided by this boundary here, right. So, when it is sampled at a particular sampling frequency which is more than twice of Fin max, then how do we get our signal? Our signal is here, which is which falls in the boundary of 0 to Fs by 2. Now, this 0 to Fs by 2 is called first Nyquist zone. From Fs by 2 to Fs, we have second Nyquist zone where we see the image of this signal. So, conjugate of that, everything will be negative here. So, you can see this here. From Fs to 3 Fs by 2 is actually the third Nyquist zone, and from 3 Fs by 2 to 2 Fs we have fourth Nyquist zone. So, in each zone you can see your signal you can receive, and you can receive the image of that signal also. Now, suppose our signal Fin max is more than Fs by 2, then what happens? As you can imagine that the signal will start from 0 to Fin by Fin max. So, the signal is here, but because we are not taking care that our Fs is more than twice of the maximum frequency, there is some aliasing of the image and the original signal. So, keeping this concept in mind, there are few benefits of oversampling and undersampling architectures which I want to discuss. What is the benefit of oversampling? For example, this is the first Nyquist zone, as I shown earlier, it is the second one, then third and the fourth one, and we want to have we want to retrieve our signal from here. This is our signal and we have filtered it. Now, this filter location is very near to the image frequency. If it becomes Fs become even little smaller, then this image will have some part inside that filter, because filters are not ideal filters, right. They do not have sharp cutoff, they can gradually go down. So, to keep our signal intact, to be able to filter it properly, oversampling is taken into account. In the oversampling, what happens, because we increase the number of samples, we increase the sampling rate, then by the Nyquist criteria our signal is here, but Fs by 2 is lying now farther from the signal and the image signal is much farther. So, we can have some loose constraint on the filter bandwidth. We can use a filter bandwidth with a large roll off factor. It can go slowly away, and in the practical conditions most of the filters are like that. They do not have sharp cutoff, they will be gradually decreasing in magnitude. So, more than that, because we have increased our Nyquist zone, so the thermal noise, it is distributed in the Nyquist zone. So, initially it was distributed in this area, the same power now it distributed into this area. So, noise goes down. In fact, the effective SNR in the case of oversampling is given by original SNR plus 10 log 10 of D, where D is the decimation factor or the oversampling factor. So, you will hear the decimation and oversampling, these two terms are used in the place of each other, and both mostly mean the same thing. So, let us take one example. Suppose you have a 12-bit ADC and let us do the 16 time oversampling with this. So, what will be the actual SNR of this system? So, 12-bit ADC, what will be the dynamic range of that one? We have SNR for the single carrier signal, original SNR. What was the formula? 6.02 into number of bits plus 1.76. So, it will be around 74 dBc. So, signal to noise ratio 74 dBc for the 12-bit. Now, we have done the oversampling by 16. So, what will happen? The new formula of the oversampling SNR will come into effect, which says the original SNR, right, plus 10 log 10 of the decimation factor, which is 16. So, the summation becomes 74 plus 12.04. So, SNR has increased almost by 10 dB or so for the single carrier. Of course, for the multi-carrier or the broadband signal, it will be lesser, but we can see the direct impact on the calculation here. So, oversampling has a certain benefits and which should be taken advantage of whenever we are designing any system. Here we are seeing the use of oversampling in practical implementation in the 16-bit DAC AD5688 from the Texas instrument. So, as you can see, first of all, our data, it is coming for the I and Q channel and it is 16-bit data being applied here. We are having from 2 to 8x interpolation options are there. So, we can choose this interpolation option, maximum we can have 8 and minimum we can have 2, or we can simply avoid this portion. But increasing the interpolation gives you good signal to noise ratio, so it is recommended that we use it. Then 32-bit NCO is being used here. So, as I told before, now in this scenario, by choosing a appropriate sampling frequency, coding it there, we are able to upconvert in the digital domain this oversampled data, which is keeping its image away quite nicely. Now, phase and gain correction are happening here because we have two different branches. So, we put this linear correction by our hand and we will be dealing with this later in detail. Now, because we have our system in the pulse form and we have the sync kind of architecture at the output whenever you have a rectangular window there, right. So, to remove the effect of that rectangular window, we multiply with the inverse of that. So, because rectangular window will actually give you sync kind of function sin x upon x. So, we will multiply with the x upon sin x to remove the effect of that one, and whatever we are getting at the output, this is what we applied to our digital to analog converter to be converted into analog domain. So, this is a practical example and we can see that we are using the NCO as well as we are using the oversampling in the actual setup. Now, this was the example for the oversampling. How we can use the subsampling or undersampling. So, let us take one example of signal which is 20 megahertz bandwidth signal, which is available from 60 megahertz to 80 megahertz, and our IF frequency is 70 megahertz. So, our RF signal, so what we are saying that in the frequency domain from 60 to 80 megahertz, our RF signal lies. So, bandwidth becomes 20 megahertz. We are told that our IF frequency is 70 megahertz. So, 70 megahertz is the IF frequency. So, how to choose our sampling frequency so that we can have the signal properly here. So, the highest frequency is highest F is 80 megahertz in the signal. If suppose I take it to the baseband, this will be the highest frequency there. So, we have to have at least twice of that, let us say, so our sampling frequency should be greater than equal to twice of F max. So, it should be more than 160 megahertz, right. So, suppose I take the 160 megahertz sampling frequency. So, Fs is equal to 160 megahertz. So, Fs by 2 will be 80 megahertz. So, in this case, if I do the down conversion, my signal will be on the boundary, right. It will be 80 megahertz, it will be 60 megahertz. So, now it is at boundary and its image will be starting right over here. It will be 100 megahertz. So, we want to avoid that, we want to have it in between. So, let us take our frequency, sampling frequency as 280 megahertz. So, f is equal to 280 megahertz. It means Fs by 2, 140 megahertz, and this is our first Nyquist zone, right, and our signal will be in between this Nyquist zone. Right. So, we are able to get the signal properly by using this particular band pass filter, and if our IF is at 70 megahertz, we will be directly getting it back at the baseband signal. Now, this was okay, this is good. We have used the oversampling, and what we have achieved, we have achieved our very clean signal in our first Nyquist sampling rate. Now, let us say I use f is equal to 56 megahertz, which is undersampling, right, because we had said that at least 160 megahertz was required to get it at the boundary. Now, we have gone to even lower, so it is undersampling. It is also called subsampling. So, again it is 56, f is equal to 56 megahertz. So, fs by 2 sorry will be 28 megahertz, and this will be first Nyquist zone. First Nyquist zone, it will be second one with 56, and the third one when I add 28 to this one. So, 84 megahertz. It will be the third zone. Now, our signal which is starting from 60 to 80 will be here. So, basically if it is folded back on into the first Nyquist region, if it is at the 0, if we remove down convert it and bring it to 0, it is folded back, then basically just by sampling in the third Nyquist zone, we are still able to achieve our signal. We do not actually have to go for the oversampling. Even with the undersampling, we are able to get our signal. Only thing is that we have to get our signal in the third Nyquist zone. So, this is the example of a undersampling example, because for oversampling we have to have high frequency, we have to put constraint on the ADC and DAC. Instead, we can use the undersampling, subsampling, and by choosing the different Nyquist zone, we can still recover our signal. Now, finishing with that, we have seen the usefulness of the subsampling and the undersampling, and the concept of RF DAC when we are directly sampling our frequency, right, which is the RF frequency. So, if we could do that, then it is actually the ideal software defined radio architecture. Now, this is one example which is called RF sampling process. In this case, in the receiver side, we are actually having directly the RF signal, we are filtering and we are directly sampling that. We have discussed before that it is not possible. It is not possible because our ADC and DAC has to qualify the Nyquist criteria. It has to have more than twice of the RF frequency. So, if the frequency of the RF signal is 1 gigahertz, then our sampling should be more than 2 gigahertz. So, it was not possible, but by interleaving of ADCs, we can actually increase the sampling rate. So, for example, our one analog to digital converter, it can support up to 500 megahertz. By using 4 ADCs and interleaving of them, we can get 4 times of that sampling frequency. So, this is the architecture which we are showing here. Our input voltage, it is applied, input signal is applied here, and they are applied to 4 different ADCs, at different sampling instances. So, in the right hand side diagram you can see that this is the clock input in the black color, and we have a clock which is starting at the 0 degree phase, and according to that at every rising edge it takes the sample, right. So, the red one it is showing that sample which it is taking. We put the next clock which is 90 degree phase shifted with respect to previous one, and again at the each rising edge it is sampling one of the sample. So, if the output of all these clocks are added together, basically we are having 4 times of the sampling with respect to the previous one. So, basically if this was the sampling instance with the red, by using all the sampling instances of different colors, we are having multiplied by 4 times of sampling rate. So, it is called interleaving of ADCs for increasing the RF frequency. In the advanced architectures we are trying to achieve that. Many companies, many RF companies, they are actually working on this principle and giving very high sampling frequency of 2 gigahertz and beyond. Now, what is the limitation? First of all, obvious limitation is that we require the extra ADC. Instead of 1 we require the 4. So, if the cost of the ADC is lower, then it is a good architecture, and in some cases we cannot avoid this complexity if we have to have that high sampling rate. For example, in the 5G under 6 gigahertz range, it is proposed that we might have to go for the signal bandwidth from 200 megahertz to 400 megahertz bandwidth signal. So, by Shannon-Nyquist theorem, we have to have 400 to 800 megahertz sampling frequency. So, this kind of structure we cannot avoid anymore. Now, what are the another limitation? Because we are using interleaving, it might not be perfect. So, there might be frequency spurs at the interleaving boundaries. So, for example, we have 4 levels, we will see this 4 images there which are at the distance which is the input frequency distance from the baseband from the 0 IF. So, we will see this kind of images there. If we have 2 level of ADC, we will see only single of this image here. To conclude, the concept of under and oversampling can be applied to achieve the manipulations for multi-rate processing and to achieve the advanced kind of architectures.